If you catch me, please remind me. Okay, okay, we're talking about central tendency today and variability. So we're continuing to characterize our normal distribution curve or any other distribution curve for that matter. So one way to do that is essentially to express the central tendency. So the central tendency is basically constituting the center of the distribution curve. It is a descriptive statistics that basically aims to represent that center. 3 markers of central tendency we will discuss. They're not the only ones, but they're the 3 most common ones. We have the arithmetic mean, we have the median, and we have the mode. And the mean, we're only talking about the arithmetic average. There's also a geometric average. So there are different ways to approach this data. The median basically constitutes the middle score that splits the data at 50% to lower than that value and 50% higher than that value. Whereas the mode is the most common score. In a perfectly shaped symmetric normal distribution, mean, mode, and median are identical. It's the same point. It's the highest peak of that normal distribution curve. So we're basically, if we estimate the central tendency, we're doing that basically here on the histogram. The data is from the so-called Charity Navigator score, which is a score which I don't know how it's being calculated, but it's basically it's a separate entity that goes through the budget, goes through the marketing strategies, et cetera, of charity organizations, of nonprofit organizations, and basically gives them a ranking or gives them a score from 0 to 100. So this is the data we'll be working with today. We're basically will use this data, and this is on your Canvas module 5 to download. We're basically calculating now first the mean, and this arithmetic mean is, as you all know from high school, calculated as the sum. So this is the epsilon, that's the sign for sum, of all individual entries of all x. So this is x1 to x40. Once you look at the Excel spreadsheet, it's 40 entries. So you would write x1 to x40. It's actually not very properly stated here by Nolan and Heinzen. So you have the sum of all entries divided by the number of entries. So what does this mean? If we open the Excel spreadsheet, please. It's basically so module 4 AP data. I should deliver chapter 4. Okay. No. Module 5. Module 5 Charity Navigator score. So here are the scores. So it's 40 scores that we're looking at.
Is this module 4 or module 5?
It's module 5. Sorry, it was my bad. I opened the wrong spreadsheet. Okay, so we have now A2 to A41 are all the individual scores. First action item I suggest for a small data set like that, click on data and let's just sort it again. Make sure that you select my list has headers because it has a header. You sort it by scores, you sort it on values, and you sort it from largest to smallest.
You're supposed to select what has headers? What if we didn't have headers, what would it say? What would happen?
Well, it would sort the header into your data and it would mix it in, which is yeah, not very favorable. Okay, so if you select my list as headers, you basically indicating if you take it off, you see, for example, if you deselect it, it includes the scores. I select it, it excludes the score, or the header, the scores header. Just make sure, because sometimes this leads to errors. Yes?
Where did you see that? Like, what did you press to first make that come up?
You go on data, you select A2 to A41, you click on data, and you click on sort. Yep.
But my list has headers, it doesn't include 97.9.
Yep. Because you said, yep, then you need to deselect it. Because it, as soon as it.
Oh, I thought that you said that we were supposed to have
Well, if you would have selected the whole thing from top to bottom, then you would need to select it. Yeah, but you're right. Good catch. So if you did not select scores, I selected scores, that's why I need to click. So my list has headers, is basically telling Excel that there's a header and it will execute the first entry. Okay, so once we sort that, essentially we get the highest score as the first entry and the lowest score. Oops.
The highest, the lowest, the lowest, the highest.
Largest to smallest. So we get as the lowest score, we get 71.5, highest score is 100. For those of you who like shortcuts on the keyboard, if you press Command on a Mac or Control on a Windows computer, you can jump from the first entry to the last entry with the cursor. It's quite useful sometimes. Yeah. Good. Okay, arithmetic mean. We want to calculate now the mean. It's the sum of all x, sum all x. This is now basically SUM, parentheses, A2 to A41. That's your sum.
Wait, how should I mean?
This is the sum first. We're just calculating the sum.
Oh,
What's the first step? Yep. So sum A2 to A41. So now you need the number of.
First,
Hmm?
you have to do the equal sign first?
Yes, correct.
Okay. Oh, okay.
And now you want the number of entries, the so-called sample size, or constant or reflected as so-called n for number. That you do, and remember the volcano example with the count function. So you do count A2 to A41. Counts exactly those 40.
Oh, and then you could do like D, mine's like D4, but you could do like D4 divided by D5, so let's do 3 on that.
Exactly. G4 divided by G5, yeah.
Let's do the equal sign.
Or G5. Yeah, so this would be equal sign, yeah. G5, for me it's 5, divided by G6. So the 3, 6, 13 divided by 40. That's your mean.
What's the difference between count and count?
Count if gives it a criterion. So for count if I only wanted to count those entries that are greater than 90, I would say count if criterion is greater than 90. So then it counts from the entire data series only those entries that are greater than 90.
So when we did it last time with frequency.
Exactly.
We didn't do greater than.
We did not, but we count if, we used count if for the number of volcanoes. You remember? For the frequency table. So that's pretty much, that's a continuation of the count function. Count will only basically count every entry that has an entry. So it will not count the empty cells. So another way to calculate the mean is also equals an average A2 to A41. And so I'm a little bit annoying with that because I'm going to calculate that with you by hand. And I will also ask you to do the same for the first homework. So all calculations, I will need to see all calculations. So no functions to the actual calculations.
When's the first homework due?
It comes out on Monday and it's due on the 21st, I believe. No, it's now wrong. 10/7, I believe. 10/7. I think 2 weeks. Yep. It will be on Canvas for you to download, and you can then play around in Excel and solve the question. Yeah. It's not. It's things that we have discussed in class, that we've done in class. Okay.
Do you repeat how we got the mean?
Excuse me.
Do you repeat how we got the mean?
We're summing up all entries. That's this.
Yeah.
We're dividing now all the entries by the number, or the sum of all entries. We're dividing it by the number of entries.
So how do you understand it?
G5 divided by G6. Okay. So this is the first marker of central tendency. What's important was to mean that we're basically at this point in time, we're basically looking at the so-called sample. So remember, we have an overall population and we have a subset of that, which is a sample. There's a difference in nomenclature in that regard. Whenever you deal and you quantify central tendency and variability in samples, you refer to them as statistics, as a statistic. Whereas if you have the same parameter in a population, it is a parameter. I'm flagging this table for important for the quiz, because on the quiz there will be questions of that kind. So sample, statistic, population, parameter, different also in terms of the terminology, the nomenclature, how to label these markers of central tendency. In a sample, you have an M or an X bar. That's basically a capital case X with a bar on top. You will see that quite frequently. In a population, it's a Greek letter mu.
Wait, can you keep it up for a second, please?
Yep.
We have to know the Latin letters.
Yep.
You do?
Yep. But it's like 3 or 4 you need to memorize, not that much. Yes, please. Yes. Open notes, you can have them on the computer, but no Googling, no messaging services, nothing. That's the only restriction. Good. So now we're getting to the second mark of central tendency. That's the so-called median. So the median basically is this middle score. This middle score basically breaks the entire data series down into an upper part and a lower part, upper 50%, lower 50%. So the way it's done, it's quite easy. For an uneven number, it's easy because then it's an actual value. Whereas when you have an even number of entries, it's a little tougher because then you need to create, you need to find the middle 2 entries and you need to divide them by 2. You sum them up and divide them by 2. So you basically build an average between the middle 2 numbers. So if we calculate now, so we're creating here now a second series that accompanies it, makes it a little easier. You just write 1, 2, 3, and then you complete the data series. You go on the right lower corner and you complete this all the way down. So you see here entry number 2, which is the largest number, and the smallest entry here was 40. Why am I doing that? Because it's just easier to find the middle score, right? So if that were an uneven number, it's easy to identify that middle score. Here it's a little trickier because it's basically here between 90.2 and 90.1. So the way I would calculate here the median is essentially the average of 90.2 and 90.1. So that's the median. That will separate your entire, so 90.15 is right in between here. All numbers above represent 50% of your data series. All numbers below are 50%, the lower 50%.
Do we have to find the middle numbers ourselves? Or is there
Yep.
a function for that?
Yes, there's a function for that. Of course, there's a function for that. And there's median A2 to A41.
Because I would think, I'm just not being smart about it. I thought the middle was between 20 and 21, not 21 and 22.
Well, that's why I labeled here on the side, because these are the first 20 entries.
Oh.
Because here's one guy. This is where the header has a weight. Yep.
How do you get the numbers?
You basically write in 1, 2, 3.
Yeah, 1, 2.
Then you select 1, 2, 3.
Yeah.
And you double click the right lower corner of the selected area. So now you find the actual numbering of each individual entry, and then it's a little easier. So you need the first 20 entries and you need 21 to 40. Yep. Okay, so this is the median. And now lastly, we have the mode. And the mode is basically the most often occurring number. So you remember when we had the normal distribution, the mode is basically the highest peak of that distribution curve. So that highest peak is in a histogram or a frequency polygon, also the most often occurring number. And this can be done, so there's a mode function, which we just found out with the previous class, equal sign mode A2 to A20, A41 gives you the mode. It's 98.2. Interesting when you look at it, because we have two numbers that occur each 2 times. Excel is here fitting through a function, and that function apparently has the highest point at 98.2. So that's why it gives you a 98.2 as the mode. Yes. Yes, I can copy the formula. It's basically equal sign mode A2 to A41.
So what is it? It's equal to this mode. Wait, what is it? Equal to
Mode A2 to A41.
Oh, it's the same thing.
Yes, 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 same concept. But the definition of the mode is that it's the most often occurring value, which constitutes the peak of this frequency polygon. So the highest value will be your mode. So you have to line them up in ascending orders, and then you just find the most frequent score if you don't want to use the function. Yes.
Well, and it's solid C, but like you can use your other numbers.
Exactly. Yes, I know. But basically, what Excel is doing, it fits a function through, and that function arithmetically gave 98.2. So there's some mathematical reasons why it takes 98.2 rather than the others. It's not really good data for this purpose. This is not really data that you would use to quantify a mode. It's not often. This is not a large data set. So, but basically what you do with the mode, you use it to characterize your distribution. And your distribution can be either unimodal, which would be a normal distribution curve. It also can be bimodal, then it has 2 of these peaks, or it can be multimodal, where you have more than 2 modes. In essence, how that looks like is sure. Unimodal, bimodal, multimodal. Sure. An example for that is here, what Nolan and Hansen is showing was the occurrence of the name Violet. So the age distribution of American girls named Violet. So it used to be quite a popular name back in the early 1900s, decreased in popularity, gained the renaissance in the early 2000s, and that's what gives this essentially a bimodal shape. So basically you have 2 modes. So that's an example that Nolan and Hansen give you for bimodal distribution. So that's basically how it looks like. So you have 2 different peaks. And in biological data, you find that quite frequently, actually. For example, when you have inflammatory markers, which you quantify for individuals, and you have one in an acute inflammation, and then you compare them to a healthy population. So there will be 2 different modes in your distribution curve when you mapped it out as a frequency polygon or histogram. So now continuing on, we're getting now to a very important topic, that is the sensitivity of these markers of central tendency to outliers. So outliers are a problem. So those of you that will do research, you will deal with outliers, and they're a pain in the neck, because unless you understand the reason why you have that outlier, it's just giving you troubles with model development, sometimes works against you in hypothesis testing. So outliers are a problem, and outliers you always need to look at in a very separate, explicit fashion, because you need to understand why is that outlier there? What does this do there? So when you look at charity navigator score, this is the charity you don't want to invest your money or you don't want to donate money to because they are doing something fishy with that money. It's one possible interpretation. So outliers are basically affecting your data. So if you have very low values, this will skew your central tendency. Most affected is the mean because it's an arithmetic measure. If you arithmetically calculate, so this is different data, it's not the charity navigator score. But when you think about the calculation of the mean, you basically sum all the values up and you divide them by the number of entries. You give each entry kind of equal weight. And if you have one value that contributes a very little numerical value to the sum, this will affect your outlier. That will affect your mean calculation quite dramatically. So generally means are very sensitive to outliers, whereas medians are not. And that kind of renders the median somewhat more useful for skewed distributions. So mean you can use for symmetric distributions. Skewed distributions always use a median. It gives a more stable estimate and a better, more solid, reliable characterization of a distribution curve. The mode is quite rarely used. In essence, I remember in my research, in my time doing research, basically only 2 examples where we used the mode. So it's really a rarity. So one reason would be if you have one particular score that is most often occurring for a good reason. Secondly, if you want to characterize your distribution, but then you look at it visually and you say, okay, so this is a bimodal, bimodal distribution as opposed to a multimodal distribution. And the third reason is when you have nominal data. So basically when you have categories and you want to quantify which of your categories, which one of your levels is occurring most often, then you would characterize it using the mode. But generally a rarity. So when you speak about distribution curves, we have now 3 markers of central tendency. Now, in addition to that, we're looking now at variability and the variability around that central tendency. The variability, basically, we will be talking only about 3 markers of variability, which is the range, the variance, and the standard deviation. Range is simple. The range is the most simple ones of those. You need to find the highest score, the lowest score, and you calculate the difference between both. That's your range of data. Easy done. By basically calculating a min, a max, and then the range is the difference between both. There's a function for that. You have with the minimal value, you have min, A2 to A41, gives you a minimal entry, which is 71.5. If you want to know the maximal value, you do max, A2 to A41.
Wait,
Oops.
Do you not have to do uppercase?
We should make a difference. Oh. The range is basically now min minus max. And this is basically this minus this. So that's your range. So that's simple, right? But it gives you
max minus min. Like in order to get the range, you do the max minus the min, not the.
correct. Yeah, I think there's a range function, but no, I'm not even sure. There may be a range function, but it's not the most common of all markers of variability. The standard deviation at the 75 percentile are more commonly occurring, which you will see in a second. So the range just gives you an idea about that span of your data, and it gives you an idea how much a problem outliers may represent in your data. So this is the range. Now we're coming from the range to the next aspect, which essentially is now a percentile. When you think of data, you basically have a min and a max. With an increase of the numerical value from min to max, you will basically characterize the percentage of entries below a certain value. So if you go from min, which is 0 percentile, to 10% to the 10th percentile, you capture with the 10th percentile a value below which you capture 10% of your data. When you look at the 25th percentile, you're capturing 25% of your data. And this is called the so-called first quartile.
So in the bottom 25%?
Yep. From 0 to 25%, this is the first quartile.
I don't know what that means though. Like what does that mean? Like, let's say this guy, let's say this I mean, it's, if we're using easy numbers, then like what would be 100? Like 100 of what? Like 100.
The number of entries. So remember how we do median?
Yeah.
The median constitutes 50%.
Yeah.
So that's the 50th percentile. So here, our 90, what was it, 90.15 at 21, this is 50%.
Okay, so in order to get.
So if I.
50%,
Yep.
Look at the median of a between 1 and 21.
Exactly. So let's start with the lower entries. So let's do here from A22 to A41. And you want to have now.
That's how it always works.
That's
the lower one.
Correct. Yeah, that's Q1. So Q1 is the lower, as per definition, Q1 is the lower one. So this is the median of A22. A22 to A41. Makes sense, right? It's quite logical when you think it through. You want to stratify your entire data set into 4 equal parts with as many entries for each of your quartiles. You just need to have those thresholds below which you basically capture 25% of your data.
Wait, sorry. Do you mind saying that again? You just do equals median of A2
to A41.
So, but then we did that, right? So now you got, yeah. And then what? Then you do A21 and A40?
Yep.
I mean A22.
You do A2 to A21. This is your 75th percentile. 75%. This is now Q3. This is median of A2 to A21. That's 94.3. So you're doing that to stratify your entire data in 4 equal parts.
I'm sorry, you might have answered this question now, but why is it A1 to A41? Not A2 to A40?
It's A2 to A21. Because we are now substratifying. So we have now the lower 50% and the upper 50%. So we stratified our data set in 2 equal parts. And now we want to know the 75th and the 25th percentile to split the entire data in 4 equal parts. So we're doing now the median of the upper and the lower 50%.
Yeah, I'm sorry. I meant under the mode, the min, max, and max again.
Oh, that's the range. That's the range. That's the first mark of variability.
What did you say that the 25th percentile was?
25th percentile is the median
Yeah.
of the lower 50%
So
of
I
the
think
data.
I got that wrong. Oh, because.
Yeah. So it's median A22 to A41.
And so why are we ignoring? Oh, we're just, okay.
We're not
We just
ignoring.
like drew an invisible line.
Exactly, kind of, yes. Well, you can color code it if you want to. You basically could make this, I don't know, yellow. And this one green. Actually, didactically a good idea. Let's do that. So that's the upper 50%. That's the lower 50%. So we're substratifying this again into 50%. Then we get 25%, 25% from 25th percentile to 50th percentile. Then we get another 25% from 50th percentile to 75th percentile. And then we get the rest greater than that up until the max. So this is Q1, Q2, Q3, and Q4. Q1, 25th percentile, Q2, 50% or median, Q3, 75th percentile. If you remember, for example, from last time, where is it now? From last time, we talked about the violin plot. You remember the violin plot? So the violin plot contains in here a so-called box whisker plot. Box whisker is called, so it basically it's represented by a box. This box here is capturing 50% of all data. So this is Q3, this is Q1. So 25th percentile to 75th percentile captures arithmetically 50% of the middle data. So that's the bulk of your data. If you think of a normal distribution, that middle part where you have all the data located around the center, that 50% is exactly in here. And if you think of the violin plot representing here the frequency polygon and the frequency of values occurring, that is what most of your data sets. All of this are kind of outliers. Not outliers, but it's basically skewing it in one direction, right? What's interesting about the box whisker plot, you have then as a continuation of that box, you have the whiskers. So think of the whiskers of a cat. You basically have those tiny little lines continuing, and the boundaries of this fine line capture altogether 95% of all the scores. So 95% of all your data is within that whisker. Everything exceeding those whiskers are shown as individual data points. It's a very elegant way to depict outliers. Any questions on that? That's quite central. So yes.
So I'm trying to understand like with the violin, like the curve of it.
So the way you have to look at it, so a violin plot and a box whisker plot for that matter, shows data on the y-axis, which is continuous in nature. But you have on the x-axis as the independent variable, you have categorically data, most likely nominal data. Think of that, for example, as something like, I don't know, blood pressure in males and females. This would be the violin for females, whereas it would be here for males. So you basically have continuous data. And when you have continuous data and you want to characterize it, you would do that with a histogram or a frequency polygon. So the way you need to interpret this is basically you would tilt it by 90%, or by 90 degrees, and you basically look here, the frequency polygon showing the occurrence of each value here on the y-axis. It's basically nothing else. It shows the distribution. Does that answer your question?
But what kind of data do you need to have in order for it to form this violin?
There would be continuous data, interval or ratio data. Yeah. You're welcome.
Can you please explain how the percentages fall out on that?
So we talked about 25th, 50th, and 75th percentile. Q1 is this value, the end of the box. Q2, the median, is that white point here. Q3, the 75th percentile, is the upper end of the box. And Q3 minus Q1 will capture 50% of your data. Does that make it clearer? And the whiskers are just a continuation of the box, basically just extending it by 22.5 points on each side. So it's capturing more data. So that only 5% are left that are representing outliers that are being shown as individual data points. Any other questions? All right. So now we have that. So now it's getting a little trickier because now we're coming to the last set of matrices for variability. We're talking now about the variance and the standard deviation. Okay. The variance. Variance and standard deviations are related to each other. The standard deviation and the variance, basically the only difference there is that the variance is the squared standard deviation. Why is it squared? Because you want to take a negative sign out of the equation. So the way you're calculating this variance is by summing the difference between each individual point x, which we have 40, minus the mean. So the mean is one constant. You calculate that once for your sample, but you have 40 different entries for each individual occurrent value. So this sum, this difference is labeled a so-called deviation from the mean. So when I will be talking about deviations, that's what I mean. When you square it, you get a squared deviation, logically. So now when you think about it, you have arithmetically, you have values that are smaller than the mean, and you have values that are larger than the mean. When you subtract the mean from those that are larger, you will get a positive number. If you subtract it from a value that is smaller than the mean, you get a negative number. So you want to remove the negative sign. That's why you square them. Once you have these deviations, you calculate then squared deviations, and then you sum all these deviations, and you get to a marker in between, which is the so-called sum of squares. And this sum of squares I'm flagging because that's a very important conceptual marker. Will kind of haunt you through the rest of the semester. Building the average of these squared deviations by dividing them by the number of entries, n, will get you to an average squared deviation. This average squared deviation is your variance. Employing the square root on this will get you to the standard deviation. We're going to do an example in a second. We're going to do that for our Charity Navigator score. The only thing I want to, let's get to that later. Okay, once again. So we're calculating a mean. We have the mean. We're calculating now a deviation from that mean for each individual entry. We're squaring this deviation to take the negative sign out of those that are negative. We're summing them up, and we build the so-called sum of squares. We're dividing the sum of squares by the number of entries, gets you an average squared deviation, which is the variance. Employing the square root gets you to the standard deviation. So it's a standardized deviation from the mean.
Could you go back to the equation for a second?
Yes. So we have here ST squared, which is one way how to show the variance. ST squared is standard deviation squared. That's the variance. we have here the sum, the mathematical operator of this, that's the sum sign, epsilon. And you sum x minus m squared. So you sum all the squared deviations from the mean up, you get to the sum of squares, and you divide them by the n. Gets you an average squared deviation. So that's the variance from the mean. So, yes.
When would someone want the variance and want the standard?
Good question. Very good question, actually, because in 99% of use cases, you will only express the standard deviation. The variance is more often conceptual metric. It's not really used often in real life. But you will always use the standard deviation. So once you employ the square root, you get to the standard deviation. Usually the way you would report your data in a paper, and that's what you will see when you read the paper, you will see the mean plus minus the standard deviation. That's the typical way of depicting that. One, if it is normally distributed. If it's not normally distributed, we talked about skewed distribution, rather use the median than the mean. So if you have skewed distributions, you will report the median and the 25th and 75th percentile. But for normal distribution that are not skewed or that are somewhat symmetrical, you will have mean and standard deviation. And this is where this is coming in. What nevertheless is an important marker is the so-called sum of squares. So this sum, which is not yet divided by the number of entries, that will also be important for analysis of variance and also for regression to some extent. So that is chapter 12 and 13, and I believe chapter 16 was regression. Okay, so let's do this. It's simple, relatively. It's a little bit more of a calculation, but once you have, so we just make a little bit more space. We take out the color coding. So let's actually make a second space. So we want to calculate now each individual deviation. So we know the mean. The mean is 90.33. How do we calculate one deviation? Easy, right? So deviation is A2 minus I5, or I7 in my case. That's one deviation. That's the deviation from the mean. So 100 is 9.6675 located away from our mean. That's our first deviation. It's basically 100, so it's A2 minus that cell in which your mean is located. Yep. Well, I'm not sure you have the same cell here. You need to know which cell you are. For mine, it's A2 minus I7. Looks like this. What did I do?
It equals what?
This. A2 minus I7. Well, I7.
There's no word in the front.
No, that's all. Well, we will need to modify it a little bit. We will need to modify it a little bit because we're lazy and we would just want to propagate that formula downwards. Okay, so this is how you calculate your first deviation. Was there a question? Do you have a question? That is impossible. Did you calculate A2 100 minus your mean, minus that cell? Yeah? Does that resolve the problem? Good. So we need to modify this formula a little bit. So we have now A2 minus I7 minus I7. And we're basically, we are locking that cell in again because we don't want the mean to shift, right? And how do we do that? We're taking the dollar sign and we're locking in our mean. So it's $I, $7. Yep. Same principle, right? We did it with the volcanoes and whatsoever. Yep. So $I, $7, or whatever cell you have your mean calculated in. Yes.
I got. If anybody has a problem with that.
Don't despair. There's a solution to that. Okay, just press escape.
What?
Press escape, go out, and revisit your formula. You want the difference of your individual entry minus that mean. That needs to be 9.67.
Like you say you equals what?
Yeah, so it's equal A2 minus $I, $7, because we're locking in the mean.
E2, what's E2?
A2 is 100. Yep, that's the first entry.
Why?
We're calculating the deviation now from the mean for each individual entry.
Oh, for each individual one?
Yep. That's why we need to lock it in with a $sign.
That's going to take a long time.
Nope, takes exactly 2 seconds.
So for each individual one?
And trust me, it takes 2 seconds, not even milliseconds.
Wait,
Okay, so
you do A2 minus $sign of whichever.
wherever your
one-
mean
whichever
is.
the mean is?
Yeah, because you're locking in the mean.
Did we want to put it over there specifically, or does it matter, or this one it doesn't matter where we put it? Like which cells that we put the deviation in, or does it matter?
It doesn't really matter, but you can be creative on that one. I'm not sure I would want to, and I wouldn't see a reason why you would
No,
want
I
to.
just put it under everything else under Duke, but now I realize you're gonna drag it down.
Yeah. Yeah, I would push this a little to the right and make space, and
I didn't get 9.667. I didn't get that number.
you did not. Okay, so
I got 7.59.
that's surprising.
I did A2 minus D6.
D6. D6 is your mean. Is your mean
2.41?
is your mean 90.3325? Ah. That's the problem. So the initial formula needs to be corrected. Okay, I would also recommend if
I
you,
don't know what's wrong. What's the sum? Oh, my sum of all the numbers is wrong.
well,
Wow, there's a lot.
just take the second one. Build a new one with average.
I don't know why, because I did sum of A2 to A41.
Yep.
What's wrong with that?
I would need to look at it.
And then when I went to it, it's 3696.4.
I don't know what to say. I would need to look at it. We need to evaluate the error. For the sake of time, I would say calculate it with the average function, which is average A2 to A41. That gives you the real mean.
The average of A2 to A41.
Correct. So this formula
The
here.
average is also 92.41. There must be something wrong with my data.
Yeah, there's something off here. Did you sort it? No.
I'm saying all of my.
What's your first entry?
100.
Yeah.
And then it goes all the way down till, oh, I see that shit.
Ah, yeah. Okay.
There was something wrong with my data.
Well.
How do I get it back to normal? Is there any
We're
way?
going all the way down, yeah? Like
Yeah.
this, yeah?
And then what?
I'm not seeing as far. What's the problem? 90.1, there's that money in 90.1?
No, it's my fault. I did something wrong.
Yeah, don't worry, just go along for now. I just copy over then the original data set. You just have to copy the formulas, or you always get that spreadsheet. Just walk along. Yes,
Send us a filled out spreadsheet,
yeah, I do.
like you said.
Yeah, I usually do. I did last time, right? You have the frequency table. For the graphs, you didn't do much, but you get them as an announcement. Check out my announcements. Yes. Okay. Yeah, we would need to look at it after. Okay, so now we have now our deviations. We're changing now A2 to $I, $7. Now we're basically just kicking that right lower corner. We're propagating this all the way down. As we discussed, after 50%, this turns in a negative number. Logically, has to. Good. Now the big problem, we're doing now the squared deviations. We're doing the squared deviations. And that's basically C2 squared. The square sign is that little hat. That little hat squares the value you give it. Yes.
So when you're pulling it down and for A1 or whatever, or A2, what's telling you to use a column? Like we didn't log in A, like why is it
Well, we did log it in. We did log it in.
for the A? No, I don't log in like me. I'm saying like for A.
Yeah, A will change, right? So this is when you pull these formulae down, this will shift. What you did not log will.
Why are we taking the numbers for A and like not for B? Like because you wrote A3, like all this.
Yeah, so it takes. So if you don't log in the A column, it will shift it down. So it will always take the same corresponding cell. And you want to do that because you want to calculate individual deviations.
So then why are we putting the dollars in by A? Like not by
Because the mean you don't want to change. You always want to subtract the same mean to get the deviation. So the mean is a constant. So you're subtracting a constant from a changing value with each row. That's why you log the constant, but not the individual value. Okay?
Why, I don't know if there's sense also, but when I scroll all the way down, my numbers are negative.
Yeah.
Okay.
Yeah, no, that's perfectly fine because this is what we're remedying now by squaring the whole operation. So we're doing C2 squared and squared. So the little hat you get with shift and 6, you get this sign. And now you're squaring it. And now you get a squared deviation. So that's 93 point something, 0.46.
Is that the variance?
No, that's a squared deviation.
Do you have to lock it?
Hmm?
No. Do you have
No.
to lock it?
No locking.
So how do you know what to lock and what not to lock?
If you subtract the constant with one cell, that one you log. The individual entry, which you want to always be a different one once you pull it down the formula, that one you don't log. You only log the constant. The constant is the mean.
So when we pull this down, you don't lock it.
Not the A column and not the C column. Now for the squared deviation, we're not locking.
What's the difference between a squared deviation and standard deviation?
Because the standard deviation is the sum of all squared deviations divided by the number of entries square rooted.
So this squared deviation is just the deviation multiplied by itself. What is that helping us with?
It takes the negative sign out and it allows you to calculate the sum of squares. This was when you were in the bathroom. Okay, so if we're pulling this down now, we're getting now the squared deviations. These squared deviations we need now to sum up, which you're doing by sum D2 to D41. That's the so-called sum of squares. And the sum of squares is a very important conceptual metric.
How did you equate it?
Sum D2 to D41.
And why did you do it?
Because we want to get to the sum of squares. So that's the sum of squared deviations. Okay, so now we know the number of entries, right? We've quantified this before. We can quantify it again. So our N is count A2 to A40, 42, now 41, is 40. So to get to our variance, we're calculating our sum of squares divided by the number of entries, which is 40. So our variance is 34.6. And now, as said, the variance is the squared standard deviation. To get from the variance to the standard deviation, you just need to calculate square root SQRT of the variance. That's all that's needed.
How did you get the variance?
By summing all the squared deviations and then dividing the sum of squared deviations by the number of entries. Yeah. That's the number of entries. So that's count of A2 to A41.
I did that, but it's not letting, it's not working.
Not working? It should be. Oops.
So just to get the variance.
So it's in principle, it's not complicated, right? It's basically no, it's not. No, but oh, what happened here? Oh. In principle, it's not complicated. You calculate the deviation from the mean, you square the deviations, you sum the deviations, get to the sum of squares, you divide it by the number of entries, and you pull the square root, and you're done. You have the standard deviation. So to go back to the lecture now, we are basically now looking at the variance. We've quantified the variance. You get that spreadsheet as an announcement. And now there's an important aspect to keep in mind. We are now looking at the standard deviation once the square root is employed. The standard deviation is a statistic in a sample. If you have a standard deviation from a population, it's again a Greek letter. And this is the Greek letter sigma.
It's a what?
Sigma,
What is that?
a Greek letter. That's just, you just need to learn like 3 or 4 of them. It's not too bad. You're not learning Greek. So, so sigma, keep in mind, because it will be stated as such in the questions. That's, yeah, it's S, it's the Greek S. So the variance is denoted as sigma squared. So this keep this distinction please in mind and don't confuse them. Yep. All right. Yeah. So we have to understand the deviation. So we know that that is a terrible order slide. I'm not sure where that comes after. So the square root of the variance is the standard deviation. Keep in mind it's standard deviation, or S for a sample, sigma in a population, standard deviation square, or MS, mean squared, for statistics, and it's sigma squared for populations. So why do we need that? Because we talked about, right? It's like you need to understand a variability and the central tendency. And if you want to accurately characterize your population as your sample population, you need markers of both the central tendency and the variability. this just will give the reader in a table, which is notably always table 1 in a paper. This would be your demographics or clinical characteristics that you want to present. You would present your normally distributed symmetrical data in that shape and form. So you would use a mean and plus minus standard deviation for symmetric data. For skewed data, you use a median and the 25th and 75th percentile as a marker. So you basically, if you would asked to present this data that we have seen here, so this is now scientific reporting. So if you do scientific reporting, okay, so this is normally distributed and symmetric. The way you would present this would be as equal mean plus minus standard deviation. For skewed non-symmetric data, you would provide it as median, and I usually do like these brackets, 25th comma or semicolon 75th percentile. So the way this would look like is, let's kind of concatenate around mean A2, A41, 2, plus minus round def P A2 to A41, comma 2. Didn't like that. Okay, I'm going to play around with this formula then. So basically, so there are ways how you can automatically retrieve this information from a cell, and you basically pack it in a format that you just can directly export it into a spreadsheet or in a Word document. Okay, any questions to anything of what we discussed? So keep in mind, we talked about mean, that's the sum of all entries divided by the number of entries. We talked about the median, which is basically the 50% mark, where basically you have like this line and you split it in 2 equal parts, greater and smaller. That basically paves the way for the 25th and 75th percentile, which basically splits these 2 equal parts, greater and smaller than the median, again in 2 parts, which gives you 4 different quartiles, equally sized, each of them containing 25% of your data. Yeah, so this is all that I had for today. If you have any questions, let me know. Yes. 1 to 4. 1 to 4. Yeah. Yes. Yes. Just give me a general comment, general thought you had when you watched that. Maybe something what pertains in your daily life. Yeah. Discussion 3. You need to look on the. I think it's on Sunday.
It's due this Sunday.
I think so. Yeah. Just look on the calendar feed.
Monday nights, because that's when we have class, or not?
I can give you an additional day. Yeah. Not for 3 now, not to Sunday, but not for 3. But moving forward, I can set them up that way. Do you have anything for
art? Like, what do you think?
yeah, that we're gonna do on Monday.
We don't have to do that yet, though, right?
Well, you can.
What? Is it
I can.
class period?
No, you can if you.
You can. Oh, I can do it before then. I don't know.
Absolutely.
Is it the
Okay,
whole
let's do it
class?
Monday, right?
Oh, thank you. But
No,
it's
it's-
on the quiz.
No. Don't worry.
Is this
Yes.
one Excel?
Hmm?
You need to do Excel on the fence.
There will not be much Excel questions. No, don't worry. Yes.
Is it gonna be the whole class time?
No, it's gonna be 20 minutes.
Okay, so, I have a peer tutor appointment tomorrow. Is there any way that the homework could be opened up early?
No, I can't do it. No.
When's the homework?
Monday.
Also, I think I missed attendance. I think I missed
What's your name?
Abigail Goldberg.
So, what's your name again?
Abigail Goldberg, okay.
Abigail Goldberg. There she is. Homework tomorrow. What time do you have that appointment?
1 o'clock.
1 o'clock. I'll look into it.
Thank you.
Sure.
If not, I'll go.
All right.
I have a question, two
Yeah.
questions. First of all, my R Studio is not working. Like I downloaded
That is a
it
problem.
and I tried to open it and I keep watching the videos and I really don't know what to do.
Do you have R installed?
I have this installed.
That's R Studio only.
I think so. And then it tells me that I can't do it.
Yeah, open.
And I try to open it. And it tells me this.
Yeah, you may have a wrong version. So there should be an announcement I made on an earlier version. Did you see that announcement?
Yeah.
Yeah, try to download an earlier version. Yes. Try to get the earlier version. That's incompatibility with your OS.
Okay.
So I don't know what OS you have on there. If you click on the Apple
Yeah.
about this Mac, yeah, you have 0 installed.
Okay, so is there one for that type?
Yes, the earlier version should work then.
Okay, thank
Yeah.
you.
You're welcome. Yes.
I didn't hear what you said about the discussion question, like what should we write for it?
General comment, general thought, maybe something where the topic pertains your life. Yeah, sure.
I was in there when you called my video attendance.
Okay.
Rachel Berger.
Yes. Oh, there she is. Got you. All right, thank you.
Wondering if you know the format of the quiz, like is it gonna be like an Excel sheet? that we have to
No.
fill out? Okay.
It's a Canvas quiz. Have you taken Canvas quizzes?
filling
It's
out
like
multiple choice?
it's fill in the blank, multiple choice, numerical values. You will have to do calculations. Now, maybe not for this one, but down the
So
road.
you bring like a calculator?
You probably should bring a
Okay,
calculator.
perfect. Thank you so much.
You can also use Excel.
Also, thank you.
Okay. Yes. Yeah. R.
Art Studio, and I downloaded it.
Okay.
I wanted a pair too. I mean, not a pair too. If there's 1,000.
Yeah, one of them actually, she, her officers, when I heard that, like, and she's like, not so related, she wants to be more, she asked me, she wants this.
That's really sweet.
Crazy. Your friend doing it. So,
You're right. That does work.
Yeah.
I'm not sure what the problem could be. What's your OS? It's not there. Catalina. Yeah, so one potential reason for that could be that your version of R, that the current version of R that you're trying to insert. Did you go on that announcement? I posted an announcement that gave a link to an earlier version of R.
Oh, okay.
Can I try it with that? You have R installed? Oh, yeah, here.
Okay. And then also, how do you like, when like you pull up the Excel sheet on the, anyway, how do you do that? Thank you.
Thank you, bye-bye. Can you repeat the question?
Like, how you open that Excel sheet for the class and like, somehow like everyone has access to it.
Yeah, it's on
there,
Canvas.
so
It's on Canvas.
where though? Because I always try to find it every class and I just
Okay.
don't know where.
Okay, so this is the module, right? So you have modules, and
Right.
the modules are organized in a way that here you have your files. So
Mhm.
under main lecture, that block main lecture will always contain chapters, articles, and navigator. So this is today's spreadsheet.
But then,
Now it's downloading.
where should I open it?
Do you have Excel installed?
I have it on like Google,
On Google.
on like my Google.
Oh, the
Chrome.
Office 365.
Yeah,
Then you need to upload it into your OneDrive.
so I should just download the Excel.
Download it from Canvas and upload it to your OneDrive.
To my OneDrive.
OneDrive. Can you open your YU Office 365?
Sorry.
That's good. No, don't worry. No, it's just an next professor. And let me just open it. Yes. No, you need to open it on. You need to open it on YU. Yep. Just open it up, and there you have the OneDrive.